There will be no season 2 of the universe, but there will be an episode 2 of this podcast. Today, Dr. Mack and I discuss the fundamental forces of nature, the tiny ovens we know as particle colliders, and why the Higgs field matters so much. Also, Dr. Mack makes me extremely anxious by introducing me to the wild complexity of protons. It wouldn't be cosmology if it didn't make me nervous. All right, here's our conversation. So the last time we talked, we got about 2 minutes in to the universe's existence. I learned that there are some hydrogen atoms that were created then that are in me now. And that provided me with a lot of comfort after you gave me a lot of early universe anxiety. So thank you.
I'm glad that it's helpful. I feel like it's nice to be star stuff, but it's even better to be Big Bang debris, right? Like, I think that's just really cool.
Yeah, I absolutely agree. But in trying to resolve that anxiety for me, which I deeply appreciate, we did skip past some stuff.
Yes.
Some fundamental stuff.
Yeah.
The fundamental forces.
Yeah, there are some really interesting cosmic evolution that happened in the very, very first few microseconds of the universe that are essential to how the universe works now and could have implications in the future for how the universe will ultimately end, which we'll get into that later on. But it's important to know that the laws of physics as we understand them now, things like how electricity works, how nuclear physics works, how, the forces that hold the nucleons inside the nucleus of an atom, the forces that allow radioactive decay to happen, the forces that govern electricity and magnetism, those are essentially universal insofar as they act through most of what we experience in the world, in the universe. But there's an important sense in which they're not universal, which is that they are energy dependent. What I mean by that is that they are different when the ambient energy, the ambient temperature is really, really high. It's kind of as if, gravity worked differently when you walked into a hot room.
Oh.
That gravity is not part of this. Gravity is a different thing and acts totally differently and is not part of this conversation. But with the other forces of nature, it is different in a really, really, really hot room. So this is why we use particle colliders.
Okay, we're about to get way more into this, but particle colliders are scientific instruments that speed up particles or tiny bits of matter and collide them together onto a target. We're going to talk about why they do that in a second.
We talk about particle colliders, as smashing protons together, that kind of thing, as though there's something interesting inside the proton that we're trying to crack into. And there are interesting things inside the proton. I'm not going to say that they're not. But the main purpose of particle colliders is to just create a really high energy environment because we know that the laws of physics are different at really high energy environments.
Oh. So when we think of the fundamental laws of the universe, those are only the fundamental laws for the universe at its current temperature, which it's been approximately at for a long time, but not for the whole time.
Yeah, exactly. And so one of the things that people talk about with CERN, the Large Hadron Collider, stuff like that, they talk about these instruments as recreating the conditions of the Big Bang. That's one of the sort of taglines. That is really what they're trying to do. They're trying to recreate the conditions of the very, very early universe when the universe was hot and dense because the laws of physics were different.
I don't want to criticize physicists on this one, but it seems like maybe y'all shouldn't have called them particle colliders if it's not primarily about the particle colliding.
Well, I mean, you have
Couldn't you have called them
hot,
dense recreators?
Just like tiny ovens?
Tiny ovens. Tiny ovens.
Yeah.
Super hot, super small. Mm-hmm. The world's smallest, hottest oven.
particles themselves are also interesting. Like, some of the early particle colliders really were trying to like figure out what the particles are made of. Like by firing electrons at protons, you can kind of probe the interior of the proton, which is fantastically complicated. Like, it is upsetting how complicated a proton is. Okay, so I'm just going to go off on a little tangent about protons because I've been doing some reading about protons because there've been some interesting results coming out recently. And my goodness, like we are lied to about atoms in so many ways. So first you get the picture that an atom is a little ball, right? Like the smallest indivisible piece of matter. That's like the ancient Greek version of an atom, right? And then you find out, okay, no, it's not actually a little ball. It's like a bunch of little balls in the middle, and then other little balls orbiting around them, right? So you got the protons and the neutrons in the middle, and then you got the electrons orbiting around in these little loops. And you've got those famous drawings of like the little balls in the center and these little loops of the electrons orbiting. Okay,
that is my understanding of an atom.
Right, and that's like the picture that takes you into like high school, right?
It got me through high school, Katie.
Sure, yeah. But then when you get into quantum mechanics in like college, you learn that electrons are actually in like a cloud of probability of electronness that sort of engulfs the atom in various ways, and the electron is not actually localized as a specific point, but it's kind of in this nebulous state. But you still kind of don't hear any more about the protons and neutrons. Those are still just kind of inside the nucleus, right? And you sort of ignore them. And then at some point you learn that a proton and a neutron, each of those are actually composed of quarks, which are a fundamental constituent of matter. So a quark is a kind of tiny particle, and you put 3 quarks together and you get a proton, and you put 3 different quarks together and you get a neutron. And the quarks are fundamental. The protons and neutrons are made of 3 quarks each.
Okay.
This is like the final thing that usually people are told about protons if they get that far.
You cannot get smaller than a quark.
Right. You can't, because quarks are fundamental. So electrons are fundamental particles. Quarks are fundamental particles. They're not divisible. There's nothing inside a quark.
No subquark.
There's no subquark, right. However, what you're told about these quarks, so the quarks come in different flavors. Then this is where this really gets really cute, right?
Yeah, up, down, strange charm, top, bottom.
Exactly, yes. Up, down, strange charm, top, bottom.
My brother wrote a song about this. That's why I know about quarks.
Right, yeah. Yeah, and it was, and when I give talks about these and get into the quarks, it's like, yeah, they were named in the 70s. It was a whole thing. Anyways, what you're told is that a proton is made of 2 up quarks and a down quark, and a neutron is made of 2 down quarks and an up quark. And because the quarks have fractional charges, you can add up the charges, and it all kind of makes sense. You add up the charges of the up quarks and the down quark, and you get that the proton has a charge of +1, and you add up the charges of the 2 down quarks and the up quark, and you get that the neutron has a charge of 0, and everything's great. It all works out perfectly. But it turns out, like, that's not how it works at all.
Really?
It's actually not true that there are just like 3 quarks stuck together in a proton. And the way that you know this, and it's infuriating, the way that you know this is that the mass of a proton, so we use units of mega electron volts to measure masses for protons and neutrons. I won't go into how a mega electron volt is defined, but it's a unit of energy that we use for mass. A proton is 938 MeV. That's the mass of the proton, 938 mega electron volts. The masses of the up and down quarks, they're a few MeV each. So you add those up and you get something like 9 or 10 MeV.
Oh, and you're missing like 920.
Yeah. You get nowhere near. So where's the other 90% of the mass of the proton, right? Because it's not enough in the quarks. And then you're like, okay, well, what else could there be in protons? And you learn about the strong nuclear force, which holds together the quarks inside the proton, holds the proton into the nucleus of the atom. The strong nuclear force, turns out, is mediated by a particle called a gluon. In the same way that electromagnetism has a photon, which is like a particle of light, the strong nuclear force carrier is called a gluon. So there's gluons inside the proton. There's quarks and there's gluons. And you're like, okay, so how much does a gluon weigh? Turns out they're massless.
Oh, well, that's a surprise to me.
Yeah.
I did not. That's like the twist at the end of Usual Suspects. I did not see it coming.
So a proton is made of 3 quarks whose masses add up to about 10 MeV and a whole bunch of massless gluons, and somehow it still has 938 MeV as its mass.
Do we know why?
Yeah. So it turns out that the mass is essentially due to the energy of the confinement of the quarks. There's some kind of there's energy associated with the way that the quarks are held together by the strong nuclear force. And also, depending on how you look at the proton, by firing particles at it, you actually find that there's a whole sea of quarks. There's a whole bunch of quarks and anti-quarks kind of popping in and out of existence all the time. And there's other quarks in there too. It's not even just the up and down quarks. You can do experiments and you can find, I think, charm quarks in protons, which is ridiculous because those weigh more than protons do.
Oh, God.
So sometimes when you do these experiments, you find quarks in there that are more massive than the proton.
Oh, God.
So none of this makes any sense at all. And the way that they do some of these experiments is by firing electrons through the proton, and they can go into the proton and penetrate into the proton. And so we're trying to figure out even how big the proton is. And there have been a bunch of new results about the size of the proton. And you do that by firing electrons or neutrinos or something into the proton, because you can just do that. You can just punch right through it with other particles. And then you find all these weird things like charm quarks just existing inside a proton, even though they're too massive to possibly be there. And so it's a whole thing about everything's sort of a superposition of existing and not existing and coming in and out of the vacuum and canceling out with other particles. It's absolutely absurd how complicated the proton is. It's kind of offensive.
I mean, you said earlier that it was upsetting, and indeed, I am very upset.
Right?
You have taken me back to a place of intense anxiety, knowing that there are a bunch of protons inside of me that sometimes way too much to be protons, and things are coming in and out of existence all the time. That's a big one.
Yeah.
Things are coming in and out of existence all the time. That's a weird situation to be in, but it is, of course, the human situation. Something like 8 billion of us are currently in existence, while around 112 billion of us have come into existence and out of it. We're only here for a little while, my friends. And that's why there's life insurance. With Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options offer same-day approval and avoid unnecessary medical exams. And with Policy Genius's licensed, award-winning agents and technology, it's easy to compare life insurance quotes from America's top insurers. So make things a little easier for those who will still exist after you don't. Check life insurance off your to-do list in no time with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. Policy Genius. We're just a bunch of atoms temporarily organized into consciousness. That's not their tagline, but it could be. Okay, so we've just zoomed all the way in and really freaked me out. Let's zoom all the way out.
It's kind of part of the story of the proton that physics works differently at different energies. So with the proton, if you fire really high energy particles at them or really low energy particles at them, the proton looks different because the interactions are changing when you're changing the energies of what you're throwing at it. And in a similar way, if you take protons and you smash them together at really high energies, you're changing how the physics of the electromagnetic force, the weak nuclear force, the strong nuclear force, you're changing how all of those forces work. And that's important because in the very early universe, the whole universe was hot and dense and at really, really high energies. And so the properties of the universe were different. The properties of physics throughout the whole universe were different because the whole universe was like the conditions inside a particle collider.
So these fundamental forces behaved differently in the early universe than they do now. So we call them fundamental forces because they are, but that maybe gives us, or gave me anyway, a sense that there's something like unchanging and unchangeable about them, which isn't quite true.
Right.
So you've named several of these fundamental forces of nature, but I have to confess that I don't totally know what they are. Can you tell me?
Okay, yeah. So there are several fundamental forces of nature. One of the ones that I'm not going to talk about right now really is gravity, because gravity seems to be something that works very differently from the forces that work on the kind of particle level.
Okay.
So let's just set gravity aside for the moment. We'll get back to it later. We'll talk about black holes and stuff, but gravity is weird. Okay, so gravity it works differently. But the fundamental forces of nature that we talk about in particle physics. Okay, so there's essentially 4 of them. Although, well, okay, electricity and magnetism seem like different forces, but they're not actually. Electricity and magnetism are both sort of instances of the electromagnetic force. So the reason that you can have things like electromagnets and dynamos is because electricity and magnetism kind of work together. They're 2 aspects of the same thing. But electromagnetism is the force that we kind of deal with the most often in daily life. Electromagnetism is responsible for electricity, magnetism, light. So light is electromagnetic waves. Photons are the carriers of electromagnetic radiation, electromagnetic energy, the electromagnetic force. So that's one of the fundamental forces. We'll call it just electromagnetism, right?
Okay.
So that's one that we're familiar with. And then there's the weak nuclear force. So the weak nuclear force is a little bit obscure. It's the thing that's responsible for particles changing into other particles in nuclear decay, things like that. So the weak nuclear force, it also has force carriers called the W and the Z bosons. It only acts at very short distances. It's important for radioactive decay, transmuting particles between other particles.
So we need the weak nuclear force to understand, like, to do carbon dating, for instance.
Yeah.
Is that right?
Yeah.
Because that helps us understand. We know how fast carbon will decay, and so we're able to date things by seeing how much it's decayed. Is that about right?
Yeah, and it acts on very short distances.
Okay.
And then the other force is the strong nuclear force. And the strong nuclear force we mentioned a minute ago because it's the force that holds particles together inside the nucleus of the atom. It's responsible for holding together protons and neutrons inside a nucleus, so like the quarks connecting the quarks inside the proton, and it has a force carrier of the gluon, which is this massless particle that kind of carries the strong nuclear force. So those are the fundamental forces of nature.
Okay.
The fact that they're called strong and weak and electromagnetism, the strong and the weak thing, the strong nuclear force is stronger than the weak nuclear force in some sense. There's a kind of hierarchy of strengths of the forces, and that's observed in how we deal with them on a daily basis. So those are the forces of nature. Now, one of the things that changes when you change the energy of the sort of the energy you're dealing with, like the energy around whatever you're measuring, is that the strength of the forces changes. And there's this effect where the forces kind of change strength so that they all become kind of the same strength at really, really, really high energies.
Oh.
And that's something that's called grand unification.
That is a good term.
Yes.
I feel like we need to just call out the bad ones. I don't think weak nuclear force is very good.
Yeah.
Because it's not very evocative for me.
No.
But grand unification.
Yeah.
Solid gold.
Yeah, so there was this effort for a long time to figure out why the forces of nature had different strengths, how they kind of interacted with each other, and eventually we came up with theories where at high enough energies they should all kind of become the same strength. They should all kind of work, together. And it turns out that as you go to higher and higher energies, what's really happening is those forces are becoming aspects of the same force.
Oh. This is getting towards some Star Wars stuff right
Yeah,
here.
yeah. Right. Well, so there's this thing that physicists do is that they try to find ways to say that things that look different are actually aspects of the same thing viewed from different angles. It's this like really satisfying thing when you can say, oh, it looks like, that's two faces and a vase, but actually you're just looking at it in different ways, and actually they're the same picture, right?
Yes, novelists also find this very fulfilling work.
Right, exactly. So this is something that physicists are always trying to do. We're always trying to make things simpler. So we don't like it when there are lots and lots of different particles. We want there to be, one kind of particle doing different things, for example. So when it was discovered that, all these different elements are actually different arrangements of the same fundamental particles, that was amazing. That was mind-blowing. The fact that hydrogen and carbon are actually just different numbers of protons and neutrons and electrons, like awesome, right? That's great. So we want to be able to do that with other things too, right? So the idea that like, oh, we have all these different forces. No, they're really the same force. They just look different because we're in this weird low energy perspective.
Oh.
That's what we really want to do. And so that's what grand unified theories are all about, is trying to say, no, we don't have all these different forces. Actually, we have one force and something happened to make it look like they're different forces. Something changed in the early universe that broke this symmetry that was all set up. Everything was all super like nicely symmetric and beautiful and perfect, and it broke at some point in the early universe, and that's why now we have all these different things.
That's why we're here, because something broke.
Exactly.
So to recap, there are 4 fundamental forces of the universe: gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. All of these forces, excluding gravity, are energy dependent, meaning that they behave differently at higher energies, and in fact, according to the beautifully named Grand Unified Theory, could actually be the same force. But where does that 4th force, gravity, fit in with this theory? Well, it turns out we don't really know. I'm gonna let Katie break that down.
And so we've got good theories to do that for the fundamental forces of particle physics, strong, weak, and electromagnetic. We haven't yet been able to do that with gravity. We're still trying. So the reason I'm putting gravity aside is because, so this is where we get into weird namings again. If you can unify the strong, weak, and electromagnetic forces, you have a grand unified theory. But if you can unify those with gravity, you have a theory of everything.
Oh.
So that's even better. That's even cooler.
Because that would explain literally everything.
Yeah. If you can get gravity to work together with the other forces, then you've solved it, right? And that's the theory of everything.
But right now it seems that gravity doesn't behave in the same way. Like you said earlier, that it's as if gravity were different in a very hot room, but gravity actually isn't different in a very hot room.
Right. So gravity is annoyingly separate from this whole picture. There are ways in which the way we understand gravity and the way we understand particle physics, quantum mechanics just don't fit together well. We don't have what's called a quantum theory of gravity. We have quantum theories of the other forces. We don't have a quantum theory of gravity. What I mean is that, like, with the other forces, we can say, oh, those forces are actually particles moving around, carrying the forces back and forth. Like you got the photon with electromagnetism, you got the W and Z bosons with the weak nuclear force, you have the gluon with the strong force. You can create a way of thinking about these forces where it's all about little packets of energy moving around, quantum particles moving around. With gravity, we haven't yet sorted that out. People talk about a particle of gravity called a graviton. That's a theoretical thing that might exist. And we can say some stuff about what the properties of that would be, but we don't have a full quantum gravity theory yet. We still talk about gravity as like actually a geometric theory. So we talk about gravity as curved space-time, and I'll get into that later on when we talk about black holes and stuff. But we have a totally different mathematical formalism for gravity than we do for the other forces. And gravity just remains weaker than all the other forces in a way that we don't quite understand, even at really high energies. So gravity doesn't get to play within the grand unified theory pool right now. So we've got gravity setting aside until we get the theory of everything, which may be something like string theory, maybe loop quantum gravity. People are working on these things. At the moment, we don't quite know how that works together with the other forces. We think that probably at some point in the very, very early universe, they were working together in some way. We need quantum gravity to understand the very, very, very beginning, because we think that at the very, very, very beginning, the forces were like all those forces were really important. You had really high densities, really high temperatures, and gravity would have been really strong while the other forces are also really strong, which is a circumstance you don't generally get. Usually if gravity is really strong, you're talking about big things like, planets and stars and, black holes. And then you're just not really dealing with particle physics anymore. You're dealing with big stuff. But in the early universe, you had to deal with particle physics and strong gravity. And so there we're going to need to figure out how gravity fits in. And we haven't figured that out yet.
Wow. Okay. Well, I mean, it's good to know that there's some work for me left to do, Katie, as I become a particle physicist with your help.
Good. Excellent. Yeah. I mean, it would be, when I first started, I was like, I want to find the theory of everything, right? That's obviously the goal, is to figure out the theory of everything, to figure out how gravity fits into all this. And anyway, I haven't managed it yet, but there's time. There's time. We'll keep working on it. Anyway, so the grand unified theory, that part we're doing pretty well with. We have a pretty good reason to believe that there was a time in the very early universe when all the forces were kind of aspects of the same force, and things happened to kind of separate them. So the really interesting, weird transition was when we changed from having electricity and magnetism and the weak nuclear force being all aspects of the same thing to those separating out. It's called the electroweak phase transition, or the electroweak symmetry breaking. So it used to be, back in the early times, back in the before times, there was no electricity, magnetism, and the weak nuclear force. There was the electroweak force. The electroweak force was something that acted like a combination of electricity, magnetism, and the weak nuclear force. And there were different particles existing in the universe. There were different forces, different particles. So these forces were not yet separate. They were aspects of the same thing, and there was a different mix of particles in the universe. And then something changed and allowed these different forces to exist and allowed the particles that we understand today to exist. And what changed was the Higgs field.
Okay.
The Higgs boson is very famous.
I've heard about it. I don't really know what it is, but I've heard of it a bunch.
Okay, so probably what you've heard is that the Higgs boson has something to do with how particles got mass in the universe.
Yes.
Right. And there's the basic explanation is that something happened in the early universe that allowed particles to have mass. And what happened was that there's this energy field through space called the Higgs field. And you can just think of it as there's like this energy field all throughout space. And you can think of it having like a value in the same way that if you're in a room, the room has a temperature. You can, at every point in space in the room, you can measure the temperature at that point. You can think of it as a field of temperature in the room, and that field has different values. And you could imagine that the room could be the same temperature everywhere in the room, and so that field has one value. But you could change that value, and you could make it from a cold room to a hot room, and that value would change. So you can think of that as like the temperature field changes, right? If you do something to the room.
Okay.
The Higgs field is an energy field that's throughout all of space, and it has some value.
And the value is constant?
Well,
oh no.
That value is the same everywhere.
The value is the same everywhere, but it's not constant throughout
the history of the universe.
History.
Yeah.
Right. Okay.
But you can imagine, like, the Higgs field is just, it's a field that's throughout all of space, and at some given time, let's say it has a value, right? The way that it changes value, that can get complicated, but at a particular time, we'll say it has some value everywhere that's the same. The important thing about the value of the Higgs field is that kind of controls how physics works in the universe. In the very, very early universe, the Higgs field had a different value. And because it had a different value, it allowed different particles and forces to exist. And then when the value changed, that changed the set of particles and forces that existed, and specifically allowed electricity and magnetism to be different from the weak nuclear force, and allowed some particles to exist that have mass.
Okay, so the Higgs boson is or is not a thing?
Yes, okay, right. Okay, so the Higgs boson is a thing. You can think of it as like a little piece of the Higgs field.
Okay.
The Higgs field is like the ocean. A Higgs boson is like a little drop of water that gets flung off in a wave, like a little bit of ocean spray.
Oh, okay. And it's really a way that we can understand that the Higgs field is there.
Yes, exactly. Yeah. So when we discovered the Higgs boson at the Large Hadron Collider, which we discovered by smashing protons together and seeing what happened, by seeing the fact that the boson was created, it told us that the field has to exist. And the field existing is really important because that tells us that our understanding of how physics changed in the early universe is really true.
Oh, okay.
The Higgs field kind of, it's you can think of it as like determining the settings for particle physics in the universe. And I won't get into like how it does that, but what you need to know is that at some point around like a few picoseconds, like 20 picoseconds, something like that, like somewhere in the very early universe, something happened that changed the value of the Higgs field. And when that transition occurred, it totally changed how particle physics works in our universe. And it allowed electromagnetism to separate from the weak force and allowed particles to get mass and kind of set everything up for the physics that we understand it today. But before that time, physics was different. Before that time, you couldn't have atoms and molecules because particles didn't have mass. You didn't have protons and neutrons and electrons. You didn't have quarks, separating out the way that we have them. You just had totally different physics. And so that change in the Higgs field allowed us to exist.
So that change in the Higgs field gave us mass, which gave us this hydrogen that's in me now.
Yeah, it allowed some particles to get mass that allowed hydrogen to exist later on. There were a couple other things that happened after that. So the Higgs field changed that allowed the electromagnetic force to be different from the weak force. It allowed some particles to get mass. Then it was still really, really hot in the universe, so there was still like soupy plasma and stuff.
That's when we had the soup.
Yeah, and so then
we talked a little bit about the plasma soup last time.
Yeah, and so the universe still had to cool down quite a lot. I mean, you still even had like quarks and gluons kind of mushed together in a soup that you didn't even have like particles separated out yet, but you had the potential for those to exist. And then, at some number of microseconds, you started to have quarks existing, and then those could form protons and neutrons. So you had those coming into existence at, around a few minutes. You started to get protons, neutrons, hydrogen, helium, a little bit of lithium. The sort of nuclei started to be formed. It's called Big Bang nucleosynthesis. That's when the universe was basically a big nuclear reactor, creating a few of the light elements, allowing the hydrogen that you are currently made of to exist as separate atoms.
Wow.
Yeah.
All right, I'm back to feeling better.
Okay, good. Good.
So you've again taken me on the journey.
Good.
And I appreciate that very much.
You're welcome.
So in the very early moments of the universe, something happened that changed the value of the Higgs field. Before that change, the laws of physics were different. And after that change, matter was able to exist. and eventually, we were able to exist. It's worth making sure we don't lose sight of how incredible it is that we are able to know with reasonable certainty what happened in the very earliest moments of our universe. And you're about to hear Katie help me understand exactly that. I'm not sure if I should feel better, but I'm also not sure after these two conversations if I should feel anything. I no longer know why I exist, and I no longer know why there is matter in the universe, which I guess I also didn't know before, but I didn't know that I didn't know it.
I mean, you kind of know that there's matter in the universe because the Higgs field changed.
Right, allowed it to happen.
And allowed matter to exist, and then nucleosynthesis happened and made protons and neutrons and so on.
Right. So the reason this is such a big deal, the Higgs boson, is because we had this theoretical idea that we ought to be able to observe this if this were true in the very early universe. And then we found experiments to try to observe it, and then we did observe it. And so something that had been theoretically described became observed, which is always super encouraging.
Yeah. I mean, it kind of fills in this story we have about the early universe, and it's fantastic how clear this story is. I mean, we're talking about, we have a really good explanation of the evolution of the universe down to tens of picoseconds after whatever the very, very beginning was, right?
I don't really know what a picosecond is, but it sounds small.
Picosecond is, what is it, like 10 to the minus 12 seconds? I'm just going to check.
That also sounds small, but I don't really have a way of imagining it.
It's a trillionth. Yeah, it's a trillionth of a second.
Okay.
So it's a real little piece of time. But yeah, a trillionth of a second. Like, it's hard to even measure that with like clocks, right? But we know a picosecond after the start of the universe, whatever it was, we know what was happening. And we can tell that story. We can say, okay, that's when this electroweak phase transition happened. And then at some number of microseconds, we had this transition that allowed quarks to separate from gluons, and you started to have these pieces that would become protons, and then a few minutes you get your first atoms, first nuclei, you get your protons and your helium nuclei, and you get your couple of lithium nuclei. Like, we've got this story, this very detailed story, and the reason that we're able to tell this story is because we can do experiments where we are successively going back in time by creating higher and higher energy collisions. So the closer that we get to those energies in our experiments, the better the story is of the very, very early universe. So when we talk about creating bigger and bigger and more powerful particle colliders, what we're trying to do is create the energies of earlier and earlier times in the universe. And because we can do that, we really know this story very, very well, and we can trace back closer and closer to the beginning. I mean, we've been able to create a quark gluon plasma, which is creating this time when the universe was so hot that you couldn't even have protons and neutrons. It was too hot for those. They were just a big mush of quarks and gluons, and the whole universe was just this big mush of quarks and gluons. We can get to that. We can get a little bit further than that, where we start to see the unification of the electromagnetic and the weak force. We're not quite at the place where they're the same force, but we can start to get toward that transition. And then we see the Higgs boson, and we know that the Higgs field existed. So we know that transition had to have happened via the Higgs field, and we're putting all these clues together, and we're creating this timeline by creating little pieces of the primordial soup in our laboratories. I mean, it's kind of astonishing that we can create this little taste, a little taste of that primordial soup, going farther and farther back in time just by smashing these particles together over and over again.
That is really beautiful. And hearing you talk about it that way allows me to glimpse its beauty in a way I haven't before. So, thank you.
Yeah, it's astonishing. I find it amazing, like how well we can understand the early universe in so many different ways, because we can look into the night sky and we can see the afterglow of the time when the universe was a hot, roiling plasma. And then we can create increasingly hot pieces of that plasma in our laboratories. And we can put those pieces together. We can say, this microwave static that we saw with this weird microwave receiver looking for stuff in space, that's connected to what we can do with colliders to recreate conditions of a hot early universe. And that all fits into the same picture of the theory of the Big Bang, of the idea that the universe was hot and dense in its early times. And we know what was happening then. And the fact that, that's 13.8 billion years ago, right? Like it's so far away in time, and it's so far away in like the experience of it. Like the laws of physics were different, the forces were different, everything was different, but we have the power to actually trace that out. We have really good evidence for how it all happened. I find that just so astonishing and amazing.
Yeah. No, it's beautiful.
And it's all where we came from, right? It's why we can exist. What we've been able to do, I think, is incredible. I think that being able to describe the first moments of the universe and have really good, really, really solid data about 20 picoseconds, after whatever the beginning was, I think that's pretty impressive. To be able to see the Big Bang directly, really, through the cosmic microwave background,
it's beyond impressive to me. It actually makes me think that humans are worth it. We're
yeah.
we're a catastrophe in a lot of ways. And it's really easy to despair about us because we're such monsters to each other, to ourselves. But then when you think about the fact that together we've worked to understand the universe to that deep degree, it really kind of gives me hope. It makes me feel like despair doesn't tell the whole story.
Yeah, it's incredibly inspiring that we are so tiny and insignificant, and yet look what we can do.
Learning about the first moments of the universe from Katie has been profound and inspiring for me. But this season of the podcast isn't only about the beginning of the universe. It's about the entire history of the universe, including the parts that haven't yet been written. So join us next time when we start to pick up the pace a little and get past, the first couple seconds. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, and mixed by Joseph Tuna-Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.